All right, time for more arithmetic with limits of sequences in particular. So remember, there's this theorem. About manipulating existing convergent sequences and talking about what the limits of the new sequences you get are. So the parts were the following. If you just multiply all the terms by a fixed constant, your new sequence converges to that same multiple of the original limit. The sum sequence converges to the sum of the original limits the product sequence converges to the product of the original limits. Ooh, I did not write the sum earlier. Sorry about that. Sorry, so this should be that right there. And then the quotient. Similar result. So this converges to the quotient of the limits. And then there's a condition for 4 that requires your denominators to not be 0. Okay, so if the sequence is defined and the quotient of limits is defined as well, then 4 is true. I'm just being a little loose here, as this is just for reminding ourselves. Okay, I want to talk about 3 here, proving that the limit of the product sequence. So every term in this sequence is a product of two terms of terms coming from a_n and b_n. So it's a_1 b_1, then a_2 b_2, a_3 b_3, and so on. That converges to the product of the two limits L sub a and L sub b. So I'm gonna do the scratch work here, sort of explain the idea, and then leave the proof to you. So for 3. Here's our scratch. What is it that we want? So things get a little complicated here because of the product, but it's not too bad, right? Let's just sort of talk it out and see where we get. So we want this at the very end. I want, right, a and bn minus the proposed limit, L sub a, L sub b, in absolute value, to be less than epsilon. Okay, great. So what do we know about? We know an and bn converge already. So we know things about an minus LA. We know things about bn minus LB, right? We can make those quantities as small as we like in absolute value. Okay, so we want to see an minus L sub a or bn minus L sub b, because we can say something precise about these quantities. Okay, so if this absolute value expression that we just wrote down can be expressed in terms of things that look like an minus LA or bn minus LB, then that's great. Okay, so how can we do that? I'm just looking at that first term there, an times bn. Okay, so I'm thinking something like this. If we had an bn, say, minus L sub a bn, that would be great because I can factor out bn and get that an minus LA expression that I wanted. So this is what we already have, right? We have this. We want to try to introduce this. So I'm just thinking of how can we manipulate the expression, and here I'm suggesting introducing this term here somehow so that we can end up with some expression that involves here an minus LA. Okay, but I have to do it without changing what we already have, right? I can't just say, okay, well, I had this original expression, I'm just going to subtract something, and now things have changed, so how can we continue from there? If we want to add something or subtract something, do it by adding 0. So do it by adding 0, add 0 to keep the same expression. Right? The equivalent expression, I guess, is what I should say. It won't look exactly the same, but it should be equal. All right, so let's go back to what we want and just see, what on earth is it that I'm talking about here. So again, we want a(n)(bn) minus limit a, limit b in absolute value less than epsilon. I was suggesting to introduce a new term so that we could factor and get an an minus la. So when I say add 0, I mean do the following. a(n)(bn), I said subtract labn. Adding 0 means just add back the same thing. Okay, so we haven't changed the expression at all. I've just written it in sort of a slightly silly looking way because it's much longer than what we had. Okay, so this is just writing exactly what we want in a different way, but in a way that allows me to do the following, right? So now, if you factor out bn, you get this. This an minus la is very, very precious to us. This is what we want. This is what we're aiming for. This is sort of what this is exactly what I was trying to squeeze into this expression. Even better, if you look at the last two terms in this absolute value now, you can factor out L sub a, and then you're left with bn minus L sub b, which is another one of these expressions that we really do want in here. Okay, this is really wonderful. So now I want to do some more manipulation with whatever's on the left-hand side. Okay, if we look at this absolute value on the left here, by the triangle inequality, this is less than or equal. I'm just going to split it into two parts. It's less than or equal to the absolute value of an minus L sub a times absolute value bn. So I sort of just split the product the absolute value of the product as well, plus absolute value L sub a times absolute value bn minus lb. Okay, so this expression on the left is less than or equal to this one I just wrote down. If I can make this expression, the last one I wrote, less than epsilon, then we're all set, right? Then it makes that our original expression on the left less than epsilon. Okay, so make this less than epsilon. Okay, so if I want all of this less than epsilon, I have this sum. How can I do that? Let's make each term less than epsilon over 2. Okay, that's the strategy. That's what we're looking for. Okay, so on the one hand, so maybe I'll talk about sort of the quicker thing on the on the right here, sort of the term on the right. So we want now absolute value of limit of a times absolute value bn minus limit of b less than epsilon over 2. This is just a constant, right? The limit exists. And we know it's a constant, so we are all set. There's a division I'm going to do here, and certainly, we should maybe talk about what happens if one of these limits is 0. But certainly, it would make the sequence, or it should make the limit come out to be 0. We can deal with that separately, but here we're going to end up with this. We want the absolute value of bn minus L sub b to be less than epsilon over 2 times the absolute value of L sub A. We can make this happen. Bn converges to LB, so we can make that difference as small as we want, right? Including less than epsilon over 2 times limit A. Okay, how do we deal with the B sub n? B sub n is bounded. Okay, so say B sub n is less than or equal to some number m. Bn converges, and every convergent sequence is bounded, so we get that. Okay, so here I'm going to write this. That means that this expression, right, that first term, is less than or equal to absolute value an minus La times m, and we want this less than epsilon over 2. Okay, as long as that's less than epsilon over 2, then the expression, right, in our inequality, an minus La times Bn, that part will be less than epsilon over 2 as well. So, in other words, we want absolute value an minus La to be less than epsilon over 2m. And we can force this to happen as well, right? Because, again, an converges to La, meaning that we can make that difference as small as we want, including smaller than epsilon over 2 times m. Right? Again, m is a constant here, that's fixed. So this is what we want to happen. So there should be some point in the sequence Bn where we can go out far enough so that we're less than epsilon over 2 times the absolute value of La. We should be able to go out far enough in the sequence An so that An minus La in absolute value is less than epsilon over 2m. We know m exists because Bn converges, right? We know La is this constant that exists because An converges, right? So all of this information is coming into play here. Okay, so this is our scratch work here. I think this tells us what we want to do. It's about piecing it together, right, and then putting together the proof of 3 here. Let's plan to discuss this sometime, right? Ask whatever questions you have, but start trying to put together a proof of this result. Okay, so exercise 6 then is to finish this proof based on this scratch work. So exercise 6 is proof 3 in the arithmetic with limits theorem. So i.e., right, A and Bn converges to LALB. And then exercise 7 will be to prove 4. Right, which is about quotients. So An over Bn, that sequence converges to La over LB. Again, there are these conditions that your denominators can't be 0 here. So that's included here. This is assumed. So just be mindful of that as well.